Google's quantum chip Willow has achieved a result that sounds almost impossible. In a benchmark experiment, Willow completed a calculation in just a few minutes that researchers estimated would take a leading classical supercomputer an unimaginable amount of time, on the order of 10 septillion years. That figure is so enormous that it is difficult to put into perspective. It is vastly longer than all of human civilization and even exceeds the age of the universe by an extraordinary margin. The chip is called Willow, and on the surface, this looks like a dramatic breakthrough in computing. But beneath the headline is a much stranger question. Where does the apparent power of a quantum computer actually come from? Some physicists have argued that quantum mechanics may involve something far stranger than the reality we experience every day. One interpretation, known as the many worlds interpretation, suggests that different quantum possibilities may continue in separate branches of reality. That does not mean Willow has opened a portal to another universe. It has not detected a parallel Earth or communicated with another reality. But its unusual computational behavior gives us another reason to examine what quantum mechanics really means. Willow contains 105 qubits, the basic units of quantum information. Traditional computers use bits. Each bit represents either 0 or 1. Every digital photograph, message, application, video, and calculation we use depends on enormous numbers of these binary operations. Qubits work differently. Through a quantum property called superposition, a qubit can exist in a combination of possible states. When multiple qubits become entangled, their states can become deeply connected, creating a system that is capable of representing and manipulating extraordinarily complex combinations of possibilities. This is what makes quantum computing so different from conventional computing. Willow was tested using a benchmark known as random circuit sampling. The experiment is not designed to solve a practical problem such as developing a medicine or predicting tomorrow's weather. Instead, it challenges a quantum processor with a highly complex sequence of operations and measures how effectively the machine can produce the expected quantum output. For classical computers, these calculations become extremely difficult as their complexity grows. Willow completed the benchmark in minutes. That result is why Google described the achievement as a major step forward in quantum computing. But this is where the real story begins. Quantum computing is not simply about building a faster version of an ordinary computer. The underlying physics is fundamentally different. In the classical world, we are used to objects having definite states. A coin is either heads or tails once it lands. A switch is either on or off. Quantum mechanics does not always work that way. At tiny scales, particles can behave as though several possibilities are present at once. When a measurement is made, we observe a particular outcome. The strange part is that physicists have debated for decades what those possibilities actually represent. One interpretation says that the alternative outcomes are not separate physical worlds. They are simply mathematical possibilities described by a quantum wave function. But another interpretation offers a far more radical explanation. The many worlds interpretation suggests that quantum possibilities do not disappear when one outcome is observed. Instead, every possible outcome continues in a different branch of reality. In one branch, an event happens one way. In another, it happens differently. According to this interpretation, all of those branches are part of the underlying quantum state of reality. Now imagine applying that idea to a quantum computer. A quantum processor does not simply test one possibility, record the result, and move to the next. Instead, quantum operations manipulate a complex combination of possible states. Interference then causes some possibilities to reinforce one another while others cancel out. Eventually, the system produces a measurable result. This is where the popular connection to parallel universes comes from. If the many worlds interpretation is correct, someone could describe a quantum calculation as involving multiple branches of reality. But that description is an interpretation of the physics, not an experimental discovery that other universes have been found. Willow has not proven the multiverse. It has not sent information across dimensions. It has not received a message from another version of Earth. And it has not demonstrated that quantum computers borrow processing power from alternate realities. Those claims go far beyond what the experiment actually showed. The fascinating part is that quantum mechanics allows these questions to exist in the first place. Imagine a problem so complicated that a single classical machine could never explore every possibility within a practical amount of time. Now imagine a quantum system representing a huge landscape of possible states and using interference to amplify the outcomes that matter. The final result appears in our laboratory. From the outside, it can look almost as though an enormous amount of hidden computation happened somewhere beyond our reach. That is one reason quantum computing has inspired so much speculation about the nature of reality. But there is another part of Willow's story that may be even more important than the benchmark itself. Error correction. Quantum information is incredibly fragile. Heat, electromagnetic interference, vibration, imperfections in hardware, and other forms of noise can disrupt the quantum state. A conventional computer can tolerate certain physical imperfections without immediately losing the information stored in its bits. Quantum systems are much more delicate. A tiny disturbance can alter the state of a qubit and introduce an error into a calculation. This is one of the biggest obstacles standing between today's experimental quantum machines and truly useful large-scale quantum computers. That is why progress in quantum error correction is so important. The goal is not simply to create more qubits. The goal is to create reliable logical qubits that can maintain useful quantum information even though the underlying physical qubits are noisy. Google's work with Willow demonstrated progress in this direction. That matters because scaling quantum computers is not useful if adding more hardware simply creates more errors. A practical quantum computer has to become more capable while also becoming more reliable. If researchers can continue moving in that direction, the future implications could be enormous. Quantum machines may eventually help scientists simulate complex molecules, explore new materials, optimize certain industrial problems, and investigate physical systems that are extremely difficult to model with classical computers.